me when you're ready.
Yeah.
No rush. Open the file. All right, welcome back for part 2 of the Polar Codes tutorial.
Okay, thank you for coming back. So last hour, we kind of left off here where we say this is how we prove that polar code has exponential decay gap to capacity and doubly exponential decaying error. And then we say that by moving the red line, you can kind of fine tune your exponent, and then if you kind of push the red line all the way to the left, you can prove the optimal error. But then you cannot retain a very good scaling exponent. So basically, you are alternating between these two possibilities where you either have a very good scaling exponent or you have very good error behavior. And then the very natural question is there any middle line? Can we find a curve that kind of interpolate between these two curves? So the short answer is that, of course, you can. You just have to dive into it and study it really hard. So here is a very simple representation of what happened here. So you begin with this one. So let's say, so here is a graph. Most of the information are irrelevant. It will be relevant later. So the horizontal axis is the exponent in the error. So when I say the error is doubly exponential, there is going to be some exponent. So I call it pi. And then rho is the exponent in the gap to capacity. So these are the two quantities that I'm interested in, and I'm kind of normalize that, taking log and normalize that by the block length such that they become kind of stabilizing the picture after n goes to infinity. And then what we are interested in is this point. So this point is 1/2. This point means that the error exponent is 1/2. And this point means that the error exponent is about 1 over 3.627. So this point is the optimal error behavior that I showed in the previous slide. And then this point is the optimal error behavior in the previous slide. And then there's like a trade-off curve between these 2 points. And the proof is this proof is in 2 steps. So in early work, this is Mondelli, Hassani, and Ubanke, they kind of present this result. So they present this this estimation, that is the location of this point, and they kind of present this whole curve by using a very simple argument that if you go back to this curve, you tell me which way you want to be. Do you want to get better error? Then I'll push the red line toward this way. Or you want to get better scaling exponent, and then I'll push the red line toward this place. So there is an optimal place that you can place the red line. And then by doing that, you can achieve every point on this curve. On the curve, my hand is shaking. So on this curve that is below. So you see that, of course, this is a very straightforward argument, and there is nothing questionable about it. But there is one thing that is unsatisfactory, namely, if you push the curve toward the left, namely, if you want better and better error exponent, you will see that there's a gap between the optimal error exponent and the optimal exponent you get if you want if you want the trade-off, and then you specialize the trade-off at this special point. So that's it. That is one kind of open problem back then, because it seems that there is something that needs to be done to at least connect these 2 lines. So I kind of attacked this problem, and then I came up with a result that basically says that yes, you can attain this curve that precisely connected to this point, and then precisely connected to this point. And then the special thing is that this curve is it's a convex conjugate of two things. So the first thing is that you have the optimal scaling exponent, and then here you have a binary entropy function, inverted binary entropy function, and then this curve sits under the binary entropy function and then shoots to that scaling exponent point when it's tangent to the binary entropy function inverted. So that's the characterization of that curve. So you can see that maybe this rings a bell, but in large deviation theory, you often see this where if you take the convex conjugate of a function that is not convex, and then you take the conjugate twice, it will get the function will be completed. Like
So is this for the BEC specifically?
For the BEC, yes. For now, let's talk about BEC.
Whatever that thing you got.
Yes, so that point that I cannot draw on this, but so that point is going to be 1/3.627, and this curve is obtained by taking the convex envelope of two things, of the two important things. So I mean, philosophically, this is kind of means a lot. Like the only thing you care is the scaling exponent and then the error behavior, because everything in between is like completed by the theory itself.
Do you know that that curve's optimal for the BEC? Like for, actually I should say for error consequences on the BEC.
Yeah, I know your question, but I didn't prove it. But if you look into the proof, it's quite optimal.
Yeah.
So there might be a way to kind of specialize, like turning over the inequality. Yeah, we can get into that, but the basic idea is that you are no longer using one red line in the plot here. So instead of using one red, we already know that this argument works, but it doesn't work well because you have to choose a place, and if you choose a place, you get this suboptimal curve. So what you did is I'm going to choose a lot of red lines. I'm going to place the red line all over the place, and then I'm to talk about how many channels that touches the forbidden zone and how many channels that doesn't touch the forbidden zone. So the upper half is like the formal definition, but the lower half is the kind of like the idea of what happens. So imagine that where is the one? Okay, so imagine that this set is the set of all channels, and then they kind of split between those channels that decided to go down to avoid the forbidden zone, or those channels that decided they want to enter the void, the forbidden zone. And then for those that enter the bottom of the forbidden zone, you do the Hofding inequality stuff here. If you do the Hofding inequality stuff here, then most of your channel will get sufficiently many squaring through the Hofding process. So you exit here because now these channels has very low z values. And then there are channels that have very bad z values, so they kind of re-enter the forbidden zone because they fail to obtain sufficiently many squaring. And then you kind of say, okay, now I'm going to recycle this channel, and then I'm going to check again whether they went down to the bottom of the forbidden zone, and then they kind of branch again. So these part of the channels, they went down to the forbidden zone, but like the second forbidden zone, not the first one. And then once they enter the second forbidden zone, you'll have another chance to apply Hofding inequality. So you apply Hofding inequality again, and then there are channels that fail the Hofding inequality, and then you recycle again, and then you kind of repeat this process for about root n steps. And so you can see this is like a direct generalization of the argument of Mondelli, Hsin, and Banke, in the sense that their argument is like stopping here. But then you can continue if you kind of extend their argument in this way, and I think this is a very natural way, then you will get a very good behavior that basically says, let's see if I have the slide. That basically says you can get the optimal scaling exponent with a very, very weak error. And once you get optimal scaling exponent with a very weak error, you apply another argument that's basically the same, but this time you are no longer recycling channels. You're going to say, okay, I'm going to apply the scaling exponent argument here. So some channels will decide that they will go to the bottom of the forbidden zone, and then there is a very, very long process of applying squaring or doubling to the erasure probability, and then eventually at almost the end of the process, some of the channel will have very good error probability. And then you apply the same argument the second time when the level is at 2 root n, and then you apply the same argument one more time when the level is 3 root n, and so on and so forth. So this is the basic idea in pictures, and then if you kind of finish fill in the combinatorial details, like how long is this segment? So there's a Hofstadter inequality with n equals this quantity, and then you control the channels that you lost, and so on and so forth. Then you will get back to this curve, this improvement of the old result curve that achieved both the optimal scaling exponent and the optimal error exponent.
Sorry, just to clarify.
Yes.
So you mean there is one curve improving that curve that you didn't plot?
So this is the old curve. This is like 16 result. But this is like 18 results. So this one is the new curve. There's a line connecting the citation to the curve. Yeah, it's not very obvious. Any other question?
I'm possibly lost. But what function are you taking the lower convex envelope on?
Like what function do I take the?
I'm possibly lost.
You mean this heel thing?
You draw a lower convex.
Oh, okay. Yes. You mean this gray curve? This one?
No. I mean on the whiteboard you have drawn.
This one.
So what function are you?
So this is just an idea. Like what happened to this curve is that there is so in gray there is this function that is a binary entropy function inverted. So this is 1 over h2z, and then this point isn't really a curve. This part is more like there's just only one point. So you put the point here, and then you kind of say what's the convex envelope of these two things. So the convex envelope is like you go from here, it used to be infinity, and then you go from here, you turn left, and then you go for this point, the tangent point, and then you go up again. And of course, it doesn't really make sense on the right-hand side. So this part means that the code becomes very bad. You have very low probability to recover any information. But this isn't very important. We are interested in this part. So that's the curve right over there.
Thanks.
Okay, thank you. Okay, let's move on. So that's the argument with pictures and precise definitions. So so you have asked several questions like, does it apply to BEC? And then the answer is yes. But then it's a good question because those argument applies to channels beyond BEC. So now let's look at what will happen if you apply large matrices to the polarizing circuit. Okay, so this is what we begin with. This you have seen this multiple times. This is the encoding and decoding contraption, and you can pay certain amount of resources to upgrade this circuit. Okay, so it's like a mobile game. So let's upgrade, and then you can So instead of 2 by 2 matrices on the left hand side, now you have 3 by 3 matrices on the left hand side, and then this whole thing will become a little bit complicated. So what happens is that you will get 3 input, and then you want to guess what is this U1 based on these 3 input, and then there's a genie that's going to tell you, hey, this is the correct U1. So based on that U1, you guess what's the best U2. And then you submit your guess, and then the genie will tell you, hey, this is the correct U2, and then you guess U3. Okay, so many steps, but it's okay. And then, so you have this 3 by 3 matrices construction, and then the next question is this going to get any better than the original proposal by Arikhan? And the answer is sadly not. So, so there are 2 choices. Either you stick with Arikhan's design, or you go 1 step further and upgrade it again. And then you can, you do all the decoding and encoding definition. So you solve for U1, and then you get the correct U1, you solve for U2, you get the correct U2, you solve for U3, and so on and so forth. And then these channels, because there are many choices for this kernel, these channels will become new channels where the erasure probability are going to be polynomial in Z, where Z is the channel you begin with. Okay, so one of the job to evaluate the performance of the polynomial is to figure out what is the correct polynomial here. And once you have the correct polynomial here, you apply the convex function argument. And you can update it again to 5, to 7, to 8. Okay, so in the previous couple slides, the magical ball is L by L matrices, such as this one I'm giving here. And then I'm going to let x1 to xl be u1 to ul. This is a row vector multiplied by that matrix. So for example, this A by A matrix. And then I'll let y1 to yl be the channel output if the input is s1 to xl. This should be an L. And then the J's new channel. So the J's new channel is the J's channel on the right-hand side will be this channel where the input you want to guess is uj and the output is y1 to yl, and also the genie will tell you u1 to uj minus 1. So all the previous bits, the genie will tell you the correct answer. And then based on this information, based on this, I should say the definition, you can compute fj of z by doing the following process. This is a very concise expression, but the process is as follows. So you begin with the channel, and then you take the columns of the channel as if it's a set. You take any subset of that columns, and then you say, I'm going to let Cj be the first be the matrix C, except that the first j rows are removed. So the picture is you begin with the channel, and then you take a subset of columns, and then you're going to remove the first j rows, and also you also have to construct another copy where you only remove the first j minus 1 rows, and then you say, if I remove one more row from j minus 1 to j, does it decrease the rank of the matrix below? And you ask this question. You kind of compute the row reduced echelon form to see if there is a pivot at the first row, and then you say, if there is a pivot at the first row, you are going to add this quantity to the final polynomial. So this quantity is a monomial that remembers the size of C. Okay, so here's the recipe. That is kind of complicated, but it's a deterministic algorithm that you can apply. And once you apply, you will get all the functions f1 to f5. And once you get f1 to f5, you can put them on the hill, and then you can bound the quantity where you evaluate the new h values and divide it by the old h value, and then you kind of upper bound that quantity to find if this constant, the constant that you obtain this way, will be the constant that correspond to the old construction of Arikhan. And if it does, it means that you kind of improve Arikan's result because now you have a better scaling exponent than what is used currently. Okay, so here is a crash course of history. These two work, Hsin, Alisha, Hai, Ubanke, and then another work, Rada, Montanari, Telata, and Ubanke, they kind of figure out that the correct value over BEC of the Arikan's kernel is that value on the left-hand side of the whiteboard. But of course, we're not interested in the precise value, so I'm just represent them by 2 points. And then in 2014, it's like a couple years after polar code are invented, we finally found a kernel that is better than Arikan's kernel. Okay, so this is kind of significant. So first of all, there is an improvement to be made. Right? We don't know. We don't know there is an improvement before this result. So they kind of show that. Okay, there's an improvement. And so, of course, if you can do 8 by 8, people will do, what about 12 by 12? What about 16 by 16? So that part is trivial. The really non-trivial part is that there isn't any channel between 2 by 2 and 8 by 8 that outperform Arikan's construction. So you think about it, this is like a magic because it's not that Arikan's kernel is optimal. It's subtly strong, but still beatable in a way. Okay, so that's what happens in 2014. And then in the following years, people have been working on larger kernel 16 by 16, 24 by 24, 32 by 32, and then the largest possible kernel is 6 by 44. Yao is currently in the audience. He showed that this thing, the scaling exponent here is 1 over 2.87. Sorry, right here. So this one is 1 over 2.87. And I don't remember the numbers in between, but something like 3.5 and 3.2 around here, and then it's finally sub 3 here. So this one is also a very interesting result in 2 ways. The first reason this is interesting is that polar code is the only code we can prove that there's a finite scaling exponent. Okay, so in a way, this kernel is like the best kernel we do, the best explicit construction we know when it comes to constructing code. Okay. The second reason this is interesting is that if you go to the work of some LDPC or specially coupled LDPC code, there's a heuristic argument that says that if everything goes well, then specially coupled LDPC code will have scaling exponent 3. So it means that I shouldn't write this down, but don't quote me on this. LDPC is about 1 over 3. And this 1 over 2.8 is better than 1 over 3. So even if you consider, even if you take into account that, oh, maybe I should accept this heuristic argument because physicists are always right, this kernel is still better. Okay, so this is the story about 64 by 64. What about the thing in between? Like there is this weird line in between. This is a work where we try to use not large matrices, but we try to use 2 by 2 matrix over F4 to achieve the same thing that other people have been chasing around. So what's that? Well, let's go back to our favorite picture. This is the construction that Arikan came out with, and then we upgrade it, except that we're upgrading it in a different direction. So this time we're upgrading it by putting 2 bits here. So now the line becomes double line. And then this double line, after multiplying this 2 by 2 matrix over GF4, the first component goes into a pair of binary erasure channels. And the second component goes into another pair of binary erasure channels. And then they go to an output processor that takes, this is 2 bits, which is the F4 element, and then there's another F4 element. So this output device takes a pair of F4 elements, and then it outputs the first guessed of the first F4 element. And then there's a genie that tells you the correct value is this particular value, and then this device will compute the second guess of the second F4 element. And by doing that, you can construct two new channels whose input alphabet is of size 4. Okay, so you start with a binary erasure channel, but then you work on quaternary channels. So what is interesting about this work is that, okay, first of all, you don't have to stay with F4. You can always go higher. You can go F8, F16, F32. And if you do the simulation, you'll find that the larger the alphabet get, the better performance they are. But there is a ceiling. There's a invisible ceiling that's somewhere between 2.5. This 2.5 is with the quotations. Like this is a simulation result. We don't have a proof. But if you go for a very large alphabet, this is what you will get. Okay, so compare this quantity with other quantity, we'll see that this one has the potential to kind of like beat the previous works. Okay, so that's the first thing. The open problem is that, can you prove this rigorously? Can you prove that? So, I mean, isn't this weird because it's not 1/2? The simulation clearly shows that the optimal value is not 1/2. So the problem is, why this particular value? And then the other problem is, can you get to this value with some mathematically rigorous proof? And the second thing that I want to comment about is that usually when we think about alphabet extension, by alphabet extension, I mean the channel you want to communicate over is a binary erasure channel, but then you work, when you do the encoding and decoding, you work on a larger alphabet. So this is alphabet extension. And usually when you do alphabet extension, there is this design pattern where you go for an inner code, and then you use that inner code to kind of process your information such that outside this inner code, it looks like an erasure channel with a very large Q. And then with this erasure channel with very large Q, you kind of apply a Reed-Solomon code that works on a very large Q. So that's the design pattern for alphabet extension. And the more precise term is concatenation, code concatenation. But what happened here is different because we are directly applying our large alphabet mechanism to the binary erasure channel. So there is no middle ground. This is bare metal. This is like, I'm going to take that as a very large alphabet channel, and then I'm going to directly work on that. And so first of all, this is not what people usually do. And second thing is that, why does it work? Well, it works because polar code never lose any capacity. The sum of the capacity is always constant. Okay, so we can afford doing things that traditional coding theory didn't do.
Can I ask
my theory, yeah.
I think maybe this notation like BEC of Z all cubed. Does this mean like, if one of the bits gets deleted, I guess I still have some partial information about what the like element of F8 is, and
sorry. This notation just means this.
Sure. Yeah. Okay.
So if you say one symbol, like this is one, this 3 bits, then this one get deleted, you can kind of see the projection onto this subspace. Yes.
And it's like, magic wand. Does that actually exploit that fact, or?
Yes, it will. Like, it basically takes, because the input is like F8. In this case, it's F8 2.
Yeah.
Right, and then you want to output
F2 to 6.
Actually, you want to output R8. So this is the tuple of posterior probabilities of every symbol.
Sure.
Yeah.
So maybe another way to say it is that you take this channel which acts on 3 bits or 2 bits if you do the thing, and think of it as a channel which acts on F4. And then do all the machinery.
I see. So it's not an erasure channel anymore. It's something
It's some complicated channel.
complicated,
It's
but I
a
can still
tetra-EC or
polarize
otherwise.
it. Yeah. Okay, I get it.
Yeah, we get that. So first of all, we get a guarantee that I think is Sasaglu proved that polar code works for arbitrary alphabet. So first of all, this will definitely work. Okay, the question is whether or not this is better than the previous, than if there is only one channel every line. So yeah, so first of all, we know it works. We just have to prove that it's better. And then in order to prove that better, we have to exploit the fact that there is BEC. It is a product of BEC. So if this is a product of BEC, the output will not be arbitrary large alphabet channel. It will be a large alphabet channel, but the error is some type of erasure pattern. There is still erasure patterns in it. It's not arbitrary real numbers. It's like you can use so 1/2, 1/4, and 1/8. And if it's 1/8, then the 1/8 is distributed in the subspace. So there's a spatial structure to be explored, and so here's an interesting graph that I drew.
Another question.
Yes.
Can you elaborate a little more on what are the simulations that you said that lead to the?
You mean this one? Let's see. So you draw a very big circuit. Okay, so there's some line. So you draw a very big circuit, but it's finite, and you got these channels, and we got like complete description of the channels. We are not simulating the input. We can characterize the channels in whole. So these channels, we put them on a concave curve and see what's the summation of each of these channels. And so there's going to be a plot where the horizontal line is n, and then this is like log of the sum of h, and then you kind of fit that with the best straight line you can have.
But there is no randomization in the structure.
There's no randomization. There is only one thing that you need to determine, namely this beginning z. So you fix z equals 1/2 because that's a very fair value. And once that has done, these channels are determinate. And so this is like a fixed quantity, and then this is like fixed quantity, and then you can do the what's that? Least square or something you want. Yeah. Okay. No question. Okay. So this is a very interesting picture that I drew to express the idea. So you see the very big rectangle is the discrete memoryless channel, which is like the arbitrary channel where the input alphabet is arbitrary, and then there is this leaf thing which says binary memoryless symmetric channels, and then on the side of the binary memoryless symmetric channel there is binary erasure channels. So this is what we used to. This is what we have been discussing about. But now, the work with large alphabet, what do we do here is that inside this discrete memoryless channel class, there is a quaternary channels, which means that channels with input alphabet 4. And then inside this, we have this special tetrahedral erasure channels, which says that, which relates to your question that we are indeed using the spectral structure of the output. We are not considering arbitrary quaternary channels. We're considering this spectral structure. And then inside this spectral structure, we define two new classes of channels, edge-heavy TECs and balanced TECs. And then we prove our scaling exponent in this area. Okay. So the trick to proving scaling exponent is that if you have to optimize your function in the very large space, it's not going to be a very good scaling exponent. So the fewer you can limit the channels, the better exponent you can prove. So that's what I want to say about larger matrices, and then we can move on to large alphabet. But before we can move on to large alphabet, we move on to binary memoryless channel, which is like the binary version of a complicated challenge. Okay, so again, we start with this diagram, and we are not upgrading this diagram anymore. We are kind of downgrading it. So we go for the hard mode, which is that now the binary erasure channel becomes binary symmetric channels, and then the output channel will be W minus and W plus. So this is just the notation for the channel. In general, these channels are non-trivial. So the bad one is still going to be binary symmetric channels, but the good one is going to be some channels that live in the larger space. And so if you kind of reiterate this construction with many layers of magical devices, then the channels will become highly non-trivial. They are no longer erasure channel. They are no longer BSCs. They're just arbitrary, generic binary channels that looks like AWGN, which is a good thing because we are familiar with AWGN, but they are not exactly AWGN. So that's the bad part. Okay, so these two channels are not simple channels. So they are not simple channels means that you have to invent new inequalities of the form where you try to express you try to find a function. First of all, you find a function that can evaluate your channel to a real number, and then you say, oh, I'm going to choose Bhattacharya parameter because Ari can choose Bhattacharya parameter. And then I'm going to say the Bhattacharya parameter of the good channel is going to be z squared, where z is the Bhattacharya parameter of the old channel. And for the bad channel, z of the bad channel is going to be in this weird interval. It used to be that there is an equality sign here, but now 2z minus z squared is just an upper bound, and then there's a lower bound. Okay, so it becomes a different problem when it comes to upper bounding this quotient, because now you look at this quotient, the denominator is 2h of z, and the numerator, one of it, this one is going to be h of z squared, which is what we had in the past. But now this one is h of something that lives between 2z minus z squared and z times square root 2 minus z squared. Okay, so now you are optimizing this quotient by finding a function that minimizes the supremum of this quotient over a space where the argument on the right-hand side is in an interval. Okay, so that's the difficult part. And so although it's kind of quite complicated, but people still manage to do that because in the end you apply power method, and then when you implement the power method, you kind of like make some very careful choice. You want to simulate where is the where should this particular value be, and then you can prove these results. So you want to bound the scaling exponent over binary symmetric channels, and the first result is by Goswami and Xia, who proves that there is a positive scaling exponent. There's an implicit number, but it's a positive scaling exponent. So it's not obvious here, but if you kind of zoom in, you will see that it didn't go all the way to the end. There's a positive improvement, and then people come after and see what they can do. So maybe some people are proving upper bound and some people are improving lower bound. And so this all happens around 2010s. And then in 2022, we made an improvement that doesn't look like an improvement because it's almost identical, but there is like a 0.7% improvement in the lower bound after like 8 years of the previous work. 8 years after the previous best bound. So what happened there? Well, the last one is interesting because we bound something different than the quotient. We bound this two-step quotient. instead of the one-step quotient. So think about that. What does this quotient mean? This quotient is in fact the square of this quotient if there are some channels that if all the channels attain the supremum of this quotient, then this will be the square of that. But the reality is that not all channels, not all z's will attain the supremum of this function, because remember there's a interval in this argument. So not all channel will attain the supremum of this quotient, means that if we consider two-step quotient, there's going to be a mismatch, and then we can get a lower bound. So the situation is like if you have a matrix using a discrete analog. If you have a matrix and then V is its eigenvector, then A squared V is going to be lambda square V. But if V is not an eigenvector, then it's going to be smaller than lambda squared V. So what we prove is that it is not possible to find an eigenvector. There is not an eigenvector, and if you can show that by doing some heavy-duty numerical computation, then you can improve the scaling exponent. But even if you do that, you can only say that there is some improvement can be made to the scaling exponent. So we kind of make the computation more precise, and we are able to get a concrete numerical improvement from 1/4.716 to 1/4.95. It's the 0.7% improvement. Okay, so that's the binary symmetric channel case, which is already hard, but it can get even harder.
You mean the other way around? You improve from 1/4.95 to 4.
No, the number is wrong. There's the 6. Yeah, okay, so this is a binary symmetric channel case, which is also all the BMS channel. And we can go even harder. We can consider discrete memoryless channels. So it's like now we are getting all the rectangle. We're considering all the channels that Shannon has considered in his innovation paper in 1948. Okay, so in this case, we still have the same problem that W plus and W minus are not simple channels. And then we have another bad news, which is that the Bhattacharya parameter doesn't work anymore. So you have to invent inequalities of the form where you're trying to compute the entropy of the bad channels and then the entropy of the good channel. And then we want to lower bound this quantity for all channels. Let me emphasize, there is an infinite amount of channels living in a space that is very abstract. We don't quite know if the space is equipped with topology or matrix. It's just some set, unstructured set. And then we want to prove this inequality. How is that even possible? But it is provable because I mean, this has been done before. Sasaglu proved that polar code can work over arbitrary alphabet if we use complicated enough kernels. But then there is this open problem, like can you optimize this whole thing like we optimize the binary erasure channel? Right? Can we optimize this inequality? Can we find another parameter? Maybe H is not the best parameter we can use. Maybe there are some parameters also not Bhattacharya parameter, maybe total variation parameter or something else. We don't know. But so this is the open problem. Okay, so it's a very difficult question, and so the next thing people do is that what if we combine these two ideas? So on the left-hand side, we have large matrices which will improve the behavior of polar code. And then on the right-hand side, we have things that will make the scaling exponent work. So what do we combine these two? We get that the optimal gap to capacity is 1 over square root of the block length over discrete memoryless channel. This is proven by, I think it began with Strawson, and then all the way, there are many people working on this, and then the latest guy is Polyansky, trying to find better and better bound and better constant. So there's a constant here. It's not 1. There's a constant that depends on the details of the channel. But in general, I'll just say it's 1 over root block length. So on the polar code side, so those are people who work on random code. On the polar code side, we have in 2019, Pfister and Ubanke proves that if you consider Q-ary erasure channel, then you can express the scaling exponent in terms of Q. And then if you let Q goes to infinity, this scaling exponent will converge to the optimal value over here. So I'm putting this dot here. And then in 2021, Fazeli, Hsin-Po, Mondelli, and Vardy proved that you don't have to let Q goes to infinity, the BEC will work. Okay. And the way the BEC work is they try to find a large random matrix, and then they find so let's see, do we have space for large matrix? So they find a very large matrix, and then they do the whole thing where let's just say, let's sample a subset of columns, and then let's delete the first j rows, and then whether or not this row has a pivot will give us a polynomial that looks like this. So if the large kernel is the random kernel, then this function is kind of like a random variable that depends on the choice of the kernel. Right? So now it's getting more and more complicated, and the notions are nested. But okay, so you have this function that are random variables that you can control its coefficient when you use the basis z to the certain power 1 minus z to the certain power. So this is also called the Bernstein basis. So you use the Bernstein basis to express a function, you control the coefficient. The coefficient is going to be, because this is a random kernel, you kind of enumerate all invertible matrices. So the coefficient is going to be related to the number of subspaces and the number of subspaces intersecting each other. So there are some Q binomial coefficient stuff there. And then they prove very strong inequality to show that the scaling exponent is 2. Okay, so now we're getting really excited because we can prove the best scaling exponent over binary erasure channel. So then people come in and prove that if you kind of extend that argument to binary symmetric channel, you can also prove the best scaling exponent, and then you can even extend that to discrete memoryless channel. So at this point, the story kind of like complete, because this is the channel that Channel has considered in his seminal paper, and then we kind of prove that polar code achieved the best possible scaling exponent over all the channels that the founding father the beat player has considered. But of course, there are more channels, but like this is like a historical milestone. Okay, so see, very good. So here is a picture of a table, and I will review the content of the table. So the table starts with the column that has probability theory, random coding theory, and then polar coding theory as its rows. And then the first thing I want to address is that there is an analog of law of large numbers, namely any channel has a capacity. Okay. The notion of capacity stems from the fact that there's an upper bound on how good you can do, and then there's a lower bound, there's a construction that shows you can indeed do that. So there is a capacity. The capacity is a number that works like the mean in probability theory. And polar code achieve capacity, which is proved by Aricon. So, okay, good. So now we kind of complete the first column. The next column is central limit theorem, which says that if you take the sum of IID random variables and then you rescale properly, and by properly I mean divided by root n, where n is a number of samples, then you get a Gaussian distribution. And the analog to this is that in random coding theory, the optimal gap to capacity you can get is also about 1 over root n. And of course, there is some works focusing on what is the correct constant instead of 1. And then after you find the precise constant, there's like, what's the lower term? Is the lower term log n? Is the lower term 1 over n? And there are works working on that. And the lower term will depend on the structure of the channel. And we just said, and we just seen in the previous slide that for polar coding, you can achieve gap to capacity that is almost optimal. So fix any constant epsilon. I can achieve gap to capacity 1 minus n to the 1/2 minus epsilon power. Okay, so now we finish the second column. There is another column that says large deviations. And so large deviation is like Hofding inequalities, but there are other inequalities. Large deviations correspond to, in random coding theory, the error exponent. So the error exponent is a positive exponent. What does it build on? It builds on the fact that the error is almost always exponential decay in n. And then in polar code, we can achieve similar thing. We can achieve exponential decay in n, except that we have to put a little sacrifice here on the shoulder of n. Okay, it's funny, but this is what we can do. And you can prove that if you use a fixed kernel, this is the best thing you can do. So there is always an epsilon, and of course, you have to ask the question like, what's the dependency on epsilon? Because otherwise, I'm just cheating. But those are for future works. So, and then we also talk about moderate deviation. So the moderate deviation is like, what's the trade-off between scaling exponent behavior and the large deviation behavior? And then there's like a convex function between them. So here is the correct up to minor term description of what random code can achieve and what polar code can achieve. And you can see that. So in this expression, E is the error, G is the gap to capacity. So the error is doubly exponential. So you take 2 logs, and G you take only 1 log. And then there's a conservation law that says that your block length is like your income. And you can use your block length to buy good error probability or buy good gap to capacity, but there is some conversion rate. You can only buy this much. And for polar code, we can do pretty much very impressively same result, except that there is some fee that we need to pay. Okay. And by paying this fee, polar code achieve this behavior of random code and also analogs to the probability theory behavior with encoding and decoding complexity n log n, where n is the block length. So this is very good because think about that. What does the polar code mean? We're not interested in using polar code in real life. We use what does random code mean? We're not interested in using random code in real life. We're interested in like proving upper bound and lower bound. And polar code come in and say, yeah, your lower bound actually are achievable using a very straightforward encoder and decoder. So kind of we're talking about solving problems. Okay, so I guess I will stop here. So I hope you are happy. And then I have a final remark that why do I put this picture here and then only talk about the top 2 and these things? Because I want you to understand that these are very interesting branches of polar code. And so basically every problem here, multiple access channel, blockheads, and wiretap channel, you can check if this table holds. Like, do you achieve gap to capacity? But then what's the capacity? Well, there's going to be a capacity region if you talk about multiple access channel or distributed compression. So you kind of like, you have to change the definition a little bit, but then you can also check if they can achieve the best behavior for these problems and these problems. And then these problems are harder, like insertion deletion channel are harder, classical commutator channel are harder. So for this channel, for example, we don't know what's their scaling exponent behavior. For this one, I think it's the same. And then there is like coded computation, which is not quite communication, but still you can use polar code to protect your computation of matrix vector multiplication. And then there's this thing, pack decoder and list decoding, which we don't even know if it achieves capacity theoretically. Of course, if we do the simulation, it is very good. But the interesting part is that you prove things, because science is about discovering the same thing using different paths. So we already know that the simulation will work. So now the open problem is that whether or not we can prove to some extent that the list decoder is good, or it is superior to a decoder without the list. So I'll stop here. Thank you very much for attending.
Thank you very much. Any questions?
On the last point, so basically, like, one question is, does it prove the scaling exponent? Do you know of any results that really
I don't know.
one way or the other?
I don't know. I said because it generalized old code, so we have the same exponent. But other than that,
Even the fact, just like Ericon's code with list decoding.
Erica's code with this. Actually, there is a subtle point. So you can imagine successive cancellation decoder as a tree decoder. So eventually you have a binary tree where, so this is what the decoder see. The decoder will see two passes, and then they will see 60% here, 40% here, and then there's like more probabilities, and eventually you want to choose a point. So this is what the successive cancellation decoder do. But the successive cancellation list decoder will so it will pick maybe this point and this point, so it will maintain these 2 points in the memory, and then he will compute whether or not these 4 points are good, and then it will select the first two. So there is a chance, very small, but there is a chance that the list decoder will choose this one. So starting from this point, the list decoder will deviate from the normal behavior of successive cancellation decoder. So you cannot assume the old analysis. And things just blow up because we don't know. Like you are sorting these real numbers, and that's not a good thing. Sorting real numbers, it's very hard to control. So the answer is the short answer is it's probably definitely better than SC, but we don't know. We cannot prove.
Yeah, I thought there were some papers claiming that it doesn't improve it, but I don't know how the exact nature of those claims, because even these limitations on scaling exponent often are only limitations on the eigenfunction, right? It's just limitation on the analysis, not the truth. So I don't know.
Yeah, there is one by Urbanki but it has a strong restriction.
Yeah, I think maybe that's the one I'm referring to.
Like a finite list size. Like, does list size 2 improve the exponent? And I think the answer is no. Okay. But like, it's list size log n could improve the exponent, or log.
That's good. I guess we kind of started the boot camp with list decoding, so I guess we can.
Sort of end it there. Any other questions? No? Going once, going twice?
If not, of course, we're not done yet. Have your lunch and be back. We have a second round of speed talks, and
Then happy hour.